So welcome to another lecture of 2DM3. We'll cover some of homework 12. So let's look at that in a moment. I just want to remind you of this. This came up in the course help channel, and I'm going to try to put it in the exercises as well. To prove a statement is true, 2 out of these boxes will work. One of them will not. Does anyone want to guess which of these boxes will not work?
Implication?
Yes. This box, P implies true. This is like saying, duplicate. I should have a table of contents somewhere. Right here. Right here. This is like saying P implies true is true. This is like saying everything is less than or equal to positive infinity. Oh, that disappeared. Sorry about that. Okay, so it's like saying a number is less than or equal to positive infinity. Every number is less than the largest number, positive infinity. So you haven't proven anything. If you want to show that a number is equal to infinity, for example, you show that infinity is less than or equal to that number. So true implies P is the same as P. Okay, so I just wanted to remind you of this this idea. You can always, whenever you are having a bit of confusion, you can try to think of the Boolean operators in terms of numbers, and then realize, wait a minute, if this won't work for numbers, it's not going to work for the Boolean operators. And the justification for this analogy is as done in assignment 2 and homework 10. They're both instances of orders. Okay, so that's why you can make these comparisons. If there's any question, please, as always, stop me and let me know. So today we're going to be we're nearing the end of quantifiers on universal and existential, and so we're going to look at an application using induction, and then hopefully on Thursday we'll wrap up quantifiers and then move on to conditionals. And there's a midterm next week, so hopefully we'll get to some of the problems that you might encounter there. I do want to mention just something in regards to the midterm. So we talked about monotonicity before. Last week I mentioned monotonicity of and or, and you have isotonicity of multiplication for non-zero numbers, isotonicity of addition for arbitrary numbers. And then we said there's some operations that have mixed tonicity in their arguments. So for instance, implication, it's monotonic in the right and antitonic in the left. So antitonic just means it flips the order around. Okay, so P implies Q and Q implies R, P implies R. This is just transitivity of implication. But you can also think of it as, I know that P implies Q, and so I have Q implies something, gives me P implies something. So the order got flipped around. It was P implies Q, now it's Q implies something with P. Okay. In particular, negation or subtraction or inverse, unary minus, these are the canonical anatonic operations. X is less than or equal to Y, so negative Y is less than or equal to negative X. Okay, so you may have seen this already. Let's see where, right down here. Okay, so M is less than or equal to N, and negative N is less than or equal to negative M. So M then N, and now it's N then M. The order got flipped around. So that's what antitonic means. It means the order gets flipped around. Okay, and you've seen contrapositive before, and contrapositive just means with respect to implication as an order on Booleans, it gets flipped around. Okay, I do want to remind some of you, you definitely need to know what orders are by now. If you're not comfortable with the idea of an order, please ask on the course help channel. It's really important to know what an order is, like going forward, especially since we've been pushing everything as an order. This pinkish table relies on the fact that the booleans are ordered by implication and the numbers are ordered with less than or equal to. We're talking about a lot of stuff that involves order. Orders are really at the core of things. Program refinement, program correctness depends on an order. We talk about propositional strength, which is on an order. The next assignment or maybe homework will be on order. The midterm will mention order. So the remaining topics to come up will be involved with orders. So please be aware of what those are and ask for help. In particular, the next assignment will or homework will mention will get you to prove theorems very similar to these ones. Okay, not these exact theorems because implication is something we've been working with for a while now. But remember, we talked about binary inverse. We said, you know what, back in assignment 1, we said you have an O plus and you can try to undo it. And so we're going to be talking about that again. Okay, and then try to prove some of these operations in that setting. Okay, ducks. Is there any questions right now? Does anyone have any concerns? Are we all good? Okay. So as I said a moment ago, transitivity rules can be thought of as antitonicity or monotonicity rules, depending on how you want to see them. So P is less than or equal to Q, and now the Q moves to the left side and P goes to the right side. But of course, this is just a transitivity rule. P is less than Q and Q is less than R, therefore P is less than R. Okay, so you've already seen some of these tonicity rules before in the guise of transitivity. They happen to coincide in particular settings. Okay. So let's pause and move to homework 12 because someone was asking about that. But are there any other questions or concerns before we do that? Algebraic?
Mathematical.
Sorry, actually, in the textbook, which chapters does it talk about orders?
Oh, I pulled those out of my head. I tried to give a good introduction to orders through assignment 2 and homework 10. If you look in chapter 15, there's some stuff on less than or equal to, and that's also really orders. But please look at homework 10 and assignment 2. Those should have the material you need. If you have other questions, I'm happy to write more content. I can. So I've already written a bunch of stuff for you in the abridged lecture notes. If need, I'm happy to add orders in here as well. I think I put them in here yet. So let me know if you want more content or if you want it in the abridged lecture notes. I'm happy to add stuff in for you. It's not a big deal. I just want you guys to have the stuff, and if that's what you want, I'll put it in. Just let me know if you need more. So I tried to make the assignment good. All right, yeah. Yes, but please let me know. And at me if I don't reply to anything right away. Okay, ducks.
Professor?
Yes.
Could you go over the last question in 7.1? That one was giving me some trouble.
7.1. I will find it, and then we can talk about it. But first, someone asked about positivity, so let's look at that for a moment, and then we'll come back to 7.1 if we have time. Does that sound right? So we're wrapping up quantifiers this week, and there will be a midterm next week, which will definitely involve quantifiers. So hopefully we'll give you maybe a small midterm prep instead of a homework or an assignment. Still not sure. Small, too long. Just about what's going on here. If Q is less than or equal to P, then in any quantification, wherever you find that Q in the body, that's going to be less than P when you change the body. Antitonicity, so this merits a little bit of a discussion. If every Q is an R, and you know some property is true for all R's, then it's going to be true for all Q's. Why is it the other way around? Does anyone want to try to give an intuitive explanation of why this is the other way around, why it's antitonic?
Mathematical.
Yes, thank you. So remember, we keep calling this thing propositional strength. Every Q is an R, right? Or Q implies R. Means if X satisfies Q, then it definitely has to satisfy R, right? And here I'm going to say, you know what? Let me work with let me prove this property about R, which is bigger than Q. Let me prove everything for R, but R is bigger than Q. Now I'm going to look at the X that satisfy Q, but if they already satisfy R, which is weaker constraints, then they can satisfy extra auxiliary constraints, which is Q. Okay. So if we know that, I don't know. I hope that was a sufficient explanation. If not, I'll augment the abridged lecture notes with more examples if that wasn't clear. I just wanted to touch on that a little bit. So let's talk about this problem that someone was asking about, disjoint range split for sigma. So this is the principle of inclusion-exclusion, right? If I'm looking at two collections, Q and R, and I'm going to add them up, you know, I go into my bag, I get something and I add it, I get another one and I add it. That's what the left-hand side says. Says, no. First, add up all the Q pieces, then add up all the R pieces. And because there's no commonality, that's okay, right? We're never gonna duplicate. I have a bag of marbles, and I'm gonna, you know, get them out randomly on the left-hand side, Q or R, or I get out all the Qs, I get out all the Rs, and then I combine them together. Okay. All right. So let's begin here. Control Alt Enter. Is this the one you were asking about, Tammy?
I don't believe I asked about a question.
Oh, you just wanted to talk about 11, homework 12 in general.
I think Alexandria wanted to talk about homework 12.
Oh, I'm sorry. I got the names mixed up. Yes. Alexandria, was this the question you wanted to talk about?
Yeah, that was me. Yeah, that one. All
right. So let's begin here for any. So let's just look at it together. There existed the sum of all X and Q, and now I'm going to add on extra pieces. Right. So I have a bag, you know, and my bag is called Q, and now I throw in an extra pieces R. So because I'm adding extra pieces, chances are the sum is going to be bigger. And because everything's a natural number, the extra pieces are non-negative, so it has to be bigger. That sounds obvious. Okay. From here to here, right? Well, I have Q or R. Ooh. What's going on here? We want to, and the next step, the next hint is we're going to apply the disjoint range split for sigma. All right. Okay, so let's see what we can do. All right, let's see what's the most obvious place to begin. If we're here, and let's just get rid of this extra line. Boop. So just go here. Disjoint range split for sigma. requires this auxiliary subproof, okay? And then it gives us a sum of two pieces. So let's get the sum of two pieces. We put that right here. Boop. Okay, let's check that out. Now we have a sum involving a Q, a sum involving an R, and we want to throw away the piece involving R. Okay, we have a rule right here. It says addition is non-decreasing, so we can apply that. Addition. Ooh, that didn't come up for some reason. Oh, I was writing lowercase. Okay. All right, that worked great. And now we just need to do this one piece. So what do we need to prove here? We need to prove that for all x, q and r is false. So for any x, we need to show that q and r is false. Oh, and that's why we gave that hint, which I deleted because I was being a bit silly. Okay, so q and r might not be false, because what if we pick r to be q? Or what if we pick r to be true? So in general, this won't be true. So what we can do here is we can say, you know what, the sum of x with something slash spot e. And then we want to pick that choice to make the thing false. So does anyone know what thing we can pick? So a handy dandy theorem. Does anyone remember it? It starts with AB, and it sounds
absorption?
like. Yeah, who said that?
Me.
I don't know who me is, but good job, me. Was that Alexandria? I don't know. I don't know who said it. So which absorption do you think we're going to need to use? Maybe this one. We take Q to be Q, and we take P to be not R, and then these guys are definitely disjoint. Can't have P and not P. So let's do absorption. Good call, me. Q. Oh. Q and sorry, we'll have R and Q, or not R. That absorption. Okay. That's the wrong absorption theorem. Oops. There are too many absorption theorems, and if you're not careful, you can get them all wrong. What did I do wrong? Oop. So this is the new feature I wanted to show you today. Let me show you the feature again, in case you did not see it. My screen is too small. So did anyone see this new warnings feature we have? If instead of absorption, I put something silly like golden rule, right? And if I try to check it, I give it a moment, it's working, and it timed out. Do you see how it timed out? Notice what happened. It put this little piece right here, and if I check again, right, it just says it came back right away. It didn't take any time. It says it's an incomplete hint, and it's not checked, so you avoid timeouts. If I try to time out and then I move my cursor around and I'm doing stuff, I'm working, I'm doing stuff, it might put that piece somewhere else. So if I'm here and I'm going to write some theorem, oh, it put it in the right place. Okay, just be careful that just be aware about it. That's all. So to avoid timeouts, it will automatically put this question mark comma, so that way we don't have to worry about timeouts. Okay, so just a new feature to get you ready. A lot of people had timeouts in the previous midterm. All right, so anyhow, we did absorption, we got here, and now we need to show for any x that you cannot have R and Q and, okay, we want to show that this is false. This is false by contradiction, and so we're done. And so here we end up with R or Q and not R. Okay. Oh, we wanted to have just a Q here. My bad. Let's rephrase this to be Q, and right here, not Q, and R. It's the same. It's the same idea. Q and not Q and R. Okay, and then this gives us our desired Q, and this one is not Q and R. So the only way to really get these is to practice them often. So nothing to be done. Contradiction and 0 of and. Okay. And it's false. Okay, that's great. We're down here. Addition is non-decreasing. Oh, oops, forgot a closing bracket. There you go. Does that help, Alexandria? Do you want to talk about it? I know we did a lot of thinking as we wrote it out. Do you want to talk about it right now, or you're good?
I'm just wondering, how did you go from the absorption, like form after the absorption to the form that you got after the subproof?
So you're asking how did I go from here to here?
Yeah.
So this range says when you have a union and you want to split it up into two pieces, you have to make sure that there is no commonality. So I took my union, and my union definitely doesn't look disjoint. It does not look like these are, exclusive pieces. So I used absorption, and I'm like, now this is the same thing, but this particular form is definitely exclusive, right? And I have to check that I cannot have the first case and have the second case at the same time. And I can't, because then I'll have Q and not Q, which is a contradiction. Does that help?
Okay, thank you.
And then here I have my desired thing plus some extra stuff. So I'll just throw that extra stuff away. Addition is non-decreasing. Okay, ducks. All right. So let's get back to the slides. So we briefly talked about strengthening and weakening. We'll come back to these again if it's not clear. And as always, I'll make you a few more of these generic ones involving O+. Then you don't have to remember so many of these rules. So like if the body is the identity, then the result is the identity. If you add 0, as many times as you want, you get 0. If you add 1 as many times as you want, you get 1. If you and true, you get true. If you or false, you get false. So instead of having to remember 4 theorems, you can just remember one simple rule. I'll try to make it less ugly. Sorry about that. So I'll make those additions and I'll put them into the abridged lecture notes for you guys. So here's another proof of the fact that the range is antitonic. So let's make use of it. So monotonicity just says in the body, if I know every P1 gives me a P2, and I proved the result is true for all the P1s that satisfy R, well, I know every P1 is less than or equal to P2, and so I know it's true for all the X's that satisfy R as well. So using 912, we can show antitonicity by first shunting in. So we have this piece. So remember transitivity of implication from the previous slide, right? So we can shunt it in, right? Then we can just apply monotonicity up here to split it up into 2 pieces, right? And then we can trade to bring the pieces back into the range position. Okay, so the proofs are not very difficult. A lot of these quantifier proofs are kind of really easy, and usually there's only one thing to do. They're so generic that there isn't that much you can do. The quantifier rules are really perhaps some of the simpler stuff to prove about because there's not much to do. But intuition is what I would like to communicate with these quantifiers. So we talked about loops last time, and hopefully we'll talk a little bit more about them in a few moments. Okay, so we've been talking about for all for a while, and existence has kind of been like on the side. That's because when you flip and you get or, when you flip less than or equal to, you get greater than or equal to, right? So they're this dual nature, and so the proofs are almost always the same. And even the book does that as well, where it's like, hey, let's talk about one of them, and then it's like, here, really quickly, a bunch of laws. Like we talk a lot about and, not that much about or, because the rules are very similar and the proofs are very similar as well. So using 927, you can prove 927A. Would anyone like a quick sketch of the proof, or you're good? The sketch of the proof is really right up here. You do almost exactly the same thing. You do trading at the very end. You do some shunting. You move some pieces around. It's not there isn't that much to do there. Okay. Hello.
Some people have some concerns in the chat about CalcCheck.
Oh, sorry. I'm on a single screen today. I didn't even see the chat. Thank you for letting me know. Let me try to get to the chat on my mobile. Some people are concerned about solutions. It looks like some solutions have been posted online. Oh, you can't load your notebook save submissions. Okay, after lecture, I'll look into that. That's unfortunate. Okay. What's with the new background? It's green. Hello, people from Core 1. Nice to see you. Ruben Lee, yes, things are always true. True things are always true. Okay. If there are things I've missed, please let me know.